All right, folks, we'll go ahead and get started. I only see a few people outside, and once they hear us, they'll probably come in. Okay, our next presentation is Jeff Smith, who's from Quantum IoT, and he's going to be telling us about machine learning for dummies. I've been looking forward to this. I can use some help.
Thanks. So thanks for coming. I know I'm between you and the bar, so I'm going to go fast and furious, but let me do a little bit of introduction to who I am and where I come from. Just to give you an idea from a neural network standpoint, I actually did my dissertation years ago in neural networks. It was on a robot that learns how to fly. It was a tail-sitter airplane that actually took off and landed like a helicopter, and then it also transitioned to horizontal flight. The mathematics that you can do on this helicopter is well known, although it's a lot faster when you have something that's only 4.5 feet tall, weighs 40 pounds, has a 10 horsepower engine on it, but it transitions, it could fly actually at 200 miles an hour like this. The problem is what you do in the in-between, and so the only way to solve those transfer equations are actually to create them yourselves and to be able to try to identify the coefficients. And so I do have a background in AI and robotics, and this particular vehicle won the first international flying robot competition back in 1991 and 1992. But we also did some other things that have to do with what we're going to be talking about today. And for instance, I worked on a process that saves the post office now about $1 billion a year because we're recognizing 1% more hand-printed characters. And what was interesting about that is that we used neural networks in order to identify those classes. And we'll talk about this a little bit during today. And how many digits are there? Most people think there's 10. There's actually at least 12. Sometimes there's 14 because you make things different ways, right? A 7, sometimes a line through it. And so by having automatic classification, things like this, you learn things yourself and you're able to train other systems to be able to increase their recognition rate. I worked at Motorola Advanced Manufacturing in robotics back in the early 80s. We did some interesting things in both speeding up the processes of robot arms and how they move to do pick and place of components and basically solving some NP-complete problems that you can't really solve in polynomial time because it's picking in place. It's really the traveling salesman problem when you're trying to place parts on a board. So that was an optimization problem we'll talk a little bit about today. I did some real-time stock trading where we took real-time information from the closed captioning, trying to look for anomalies there where people actually made mistakes on the symbol relative to the news, and then did backwards trading on that. And then today I'll also talk a little bit about, quickly about Catapult Health, Studio Movie Grill, a large soft drink manufacturer. We've done some work with a petrol C-store company, and we've also done some interesting IP stream classification in a retail environment, basically looking at real-time data off of Wi-Fi networks to find out and classify the types of data that they're actually looking at without knowing the data and just looking at the way the data actually is moving back and forth rather than being able to look at the content itself. Whoops. Just to let you know that I have a sense of humor. My original dissertation title, which I wanted to be the longest, each of the letters actually spell "Don't worry, be happy." Okay, and unfortunately, my senior professor was smarter than me, and he's noticed it. Okay, and I had to change the title. So the Quantum IoT story is that we're a IoT SI. That's the one floor elevator speech. So we're a systems integrator in IoT. I have a background in this IoT business. I actually started a company called Sensor Logic that was purchased by Gemalto, started a company called Ublip that was purchased by Numerex, became the chief technology officer Numerex. Previous to that, I started a company called OnRamp that became a pretty good sized ISP. We ended up selling it as Vario to Nippon Telephone and Telegraph after a successful IPO. Quantum IoT does analytics and applications and systems integration, building things together, but we also host applications for people inside the cloud and also have network operations and DevOps capabilities. So what types of problems are really associated with machine learning? So, what are the coefficients, that I need to fly when I'm not really a helicopter or an airplane? In food and movie service, how much food should I prepare? We have a large client, Studio Movie Grill, that has 30 Cineplexes around the United States, 300 theaters, and their largest item is food waste, right? But they want to optimize other things, like, for instance, they want to know who their optimum servers are. So there's a ranking that needs to happen there. Well, using machine learning, you can take all of that data about those servers and be able to do an automatic ranking to be able to know how and who should need to train the other people in order to increase your performance within those stores. And then from a classification standpoint, which we'll spend a lot of time on classification, or, is this a high-risk patient? We have a healthcare provider for remote healthcare, and that is a key indicator. And not only that, but there's another layer that we're working on in research and development, which is really during a consult, which is in a televideo session on a laptop computer that's located at the work site in order to do a health and wellness survey, the person is there. And so there's a lot of available technology that's basically machine learning based through Watson and Azure, and we'll talk about those, to do things like facial recognition. Well, there's also the capability to apply that to stress recognition, and there's also voice recognition and voice stress analysis. Now, if you combine those two, you have the ability to be able to, while the consult is going on, to know where there's little sensitive areas, right? And then be able to do classification of those people into groups so that you can have the right questions to ask specific to a group or population of people. And that's a classifier. Other classifiers are things like fraud detection, which we'll talk about the fact that what you really want to do in fraud detection is not really try to detect fraud, because that's hard, okay? What you want to do is detect whether it's a good transaction, okay? And then the fraud is the anomaly, because it's very difficult to train on fraud, right? And we'll talk about that. So what traffic is going over my network? Talked about that for a minute. Who's the best server? Talked about that. And is the correct stock on my shelf, which is really a image processing problem. So this is a case study of which my cohort Ken has some of these available if you'd like to read about the case study or go online to the Quantum IoT website. But it goes into some specific details about the Catapult Health story and some specific details about Studio Movie Grill and ACP International, which are three of our case studies that are online. So what's learning? Well, it's really a change in a system in order to prove its performance. I happened to, during my work in AI and at the AAAI show, where I got this really cool button that says artificial intelligence is better than none back in 1986, I met Herbert Simon. Herbert Simon is one of the grandfathers of AI. And and Marvin Minsky also was there. But Herbert Simon, learning denotes changes in a system that enable it to do, maybe the same task a little bit better. And Marvin Minsky, who has said lots of interesting things, and I had the opportunity to entertain him for dinner in Dallas one time. But he said learning is making useful changes in our minds, but it's also, from a machine standpoint, the same thing. So what's machine learning then? Well, machine learning is really the study of the algorithms that are used in order to improve some kind of performance with some task with experience. So you do something and hopefully you get better at it. And optimization of the performance criterion over some particular time. What's the role of statistics? Well, what you find out, frankly, whisper this, if you took statistics, frankly, this stuff should be relatively straightforward, even if you didn't. Realize that a lot of what this is really nth order statistics. It's really, in some cases, a lot of the algorithms that are used are nonlinear algorithms of applications of linear algorithms like regression, and we'll talk a little bit about that. And then what's the role of computer science? It's basically to try to implement those types of algorithms. These slides, by the way, will be available to you, so I expect that in some cases you'll move up to the, oh, I've seen that before, from I've never seen that before, or from I've seen that before to I kind of understand it. And as you move up that, maybe you can go through these slides a little bit more. You can use it as a reference. So machine learning really is about many different pieces of this. I particularly got into it through control systems and controlling robotics and things like that. But a lot of people get into it from statistics or from data mining. Some people come from the psychology side. Some people come from the cognitive sciences side. Some people are trying to mimic the way the brain actually does things with neural networks and things like that. And some people actually come through it from places like the Boltzmann machine that has to do with simulated annealing, which really has to do with people that really understand things like how to make steel. And it's kind of interesting about how that can apply to models of learning. So isn't linear regression just statistics? Or yeah, it is. Linear regression really is just statistics, and so is the linear regression that's used from a machine learning standpoint, just statistics. But the idea here in a regression is really where you get in, you put in something and you get out a value. Okay, you don't really classify it. You're basically getting a value for something you put in. And linear regression, where you can actually have a line, or nth order is maybe it's not a line, maybe it's a vector that's in space. And a while back, I worked at the Superconducting Super Collider with a whole lot of really smart people, and I was fascinated when you'd have like lunch with some people that were Nobel Prize-winning physicists working on one of the largest particle accelerator projects in the world, and they would start talking about n dimensions, and I'd be like, I really just want to eat my lasagna. But so really linear regression, simple linear regression. There's ordinary least squares, gradient descent. All these things can be done on a spreadsheet. That's a good place to start, frankly, to be able to find out how you can predict the future, basically by taking a bunch of statistical samples of the past. Traditional programming is data and program go into a computer and you get an output. Machine learning is a little bit different. You get the data and the output and you train it with an algorithm, and then you get out a program. So it's quite a bit different from a architectural standpoint. So what is that learning system? You've got a learning element, so some algorithm that you're using in order to do the taking the error from the training set and what your expected outcome would be and feeding that back. And then you have some performance element which has some knowledge of what the thing should be. In most cases for this, those training elements are really a set of known values given a set of inputs. And then you have a problem generator that generates those problems. And frankly, in most cases, the problem generator is not generating like a control system that's with a robot that's actually moving. What it really is it's a set of data. So you have a set of data, and you're trying to put it into the system. You take a portion of that data as a training set. You take the rest of the data as a test set, and then you find out how well you've done with that particular algorithm. So three really types of characteristics in the learning system we'll talk about. We'll talk about supervised learning, where examples are labeled, and labels just mean you know what the output is. You have unsupervised learning, where you really don't have any labels. You don't know what the answer is supposed to be. And then you have reinforcement, which is reward-based learning. There's a great example in Google on the web, which is a reward-based system for a program that learns how to play Breakout. And what's cool about it is at the end of the breakout session, the thing actually figures out that if you get the little thing all the way up and it starts going back and forth like this, that's what you need to do to win. And what's fascinating about that was not programmed in at all. That was something that the thing actually, through reward, was able to figure out. And the figuring out part was not through very many iterations of it. So from a representation standpoint, what you'll find out is that knowledge can be represented in lots of different ways. Decision trees are one way. We'll show examples of that. Sets of rules or logic are another way. I won't go through that very much because it's not used that much. You have instances, which are really the training sets. You have graphical models like Bayesian and Markov models, which were well known from a mathematical standpoint. You have neural networks, and there's lots of different types of neural networks, but the primary feed-forward neural network is one that was based originally on a perceptron that Hinton basically did, that everybody knows is backpropagation now. And then you have support vector machines, which are really another statistical way in a nonlinear and n-dimensional space in order to provide some very, very fast trained outputs with some pretty reasonable reasonable results. And then you have some things like Bayesian models that are probabilistic in nature applied to the same sorts of support vector type models. And then you have model ensembles. And you hear this word a lot, and sometimes in computer science and in engineering, as you all know, we just throw out words and to try to impress people with how smart we are. But, and there are a lot more simpler words. But really what ensemble is basically using a combination of these things. There's evaluation, different types of ways that you can evaluate these types of models. And mean squared error is probably the most common way to do that in statistics. But there are other ways to do that in machine learning. And then from an optimization standpoint, that's really what you're trying to do. You're trying to take this space and think of it as in 2 dimensions. It's really a board, okay? And the board has a bunch of pits and valleys inside of it. And you have and take a ping pong ball and throw it on the board. And what you really want to do is you want to shake the board in such a way that the ping pong ball goes to a minimum. Okay? And so that's the optimization problem. How do you get the ping pong ball to the minimum in that state space? So from a training and testing standpoint, typically what happens is you have a training set. We have known values, like the red and the green, or the blue and the red over here, and you have some linear function, maybe it's linear, that you have the ability to be able to separate those two. So what can we do in order to provide a algorithm with a subset of this universal set of stuff and shove it in the algorithm with, hey, if I give you this, okay, you need to tell me whether it's red or blue, okay? And what you really want is in a linear standpoint, you really want that line, right? You want to identify that line. And that line basically is, are you at the bottom of the line, or are you on the right of the line, or on the left of the line? That's all you want. It's just a yes-no proposition. Now a classifier, that's basically a classifier with, basically one output, yes or no, okay? Now classifiers can be in dimension. And so we'll talk about the fact that you might want to classify things into, like for instance in the healthcare example, you want to classify things into, oh, this person has a high propensity for diabetes, this person has a high propensity for some other disease or things like that, and you're basically trying to classify them into lots of different groups. And that's if you know the groups beforehand. The other thing to do, and is really, and this is what we did with the data that was coming in, real-time streaming from STPs in a cellular network, and that was taking the control channel data, this SS7 data for SMS messaging, and actually taking a real-time stream of this data and be able to go, you know what? I know this is data from a whole bunch of IoT devices, and I know that one of them is going a little crazy, but I have no idea which one it is. And so classifying these, because these are all things that are doing different things. Like one may be, connected to a car and it's tracking a car around here. One may be in an alarm system and it only reports a couple of times a day. One may be, something that's reading the temperature off of something. One may be in a winery, out in the field measuring humidity. And they're all IoT devices, right? But as a telecom provider, we're wanting to figure out which one of these things is going off into the weeds. They're all very different. And so what you want to do is you want to basically automatically create these groups of these things. So supervised learning, unsupervised learning, and reinforcement learning. So supervised learning algorithms, there's things like decision tree induction. Induction just means we figured it out. It was induced from something that we did from a training set. We induced a representation of knowledge about the system. And the ultimate brain dead in an induction tree mechanism is creating this tree. In fact, we'll get to an example of it. And it's like, oh, we're going to separate it into one element per little block in a tree. Well, that's crazy. I'll show you exactly what I'm talking about in just a second. But there's also, as I said, Bayesian neural network and some other, and then we'll talk a little bit about clustering algorithms. One of the things I really want to make sure that I emphasize, though, is dimensionality is key. And so the next 6 slides actually have to do with this concept of dimensionality. And the reason why it's a problem is because if you have a hugely multidimensional space, then it's very hard to train the system, particularly when those things actually overlap and they're not orthogonal to each other, where things will line up or something like that. And you have more data and more training that you really need. Okay? So what you really want to do is you want to have data elements that don't have anything to do with each other. And that's what that orthogonality means. Orthogonal is sort of the mathematical meaning of it doesn't have anything to do with it. And then, so this is an example of sort of the complexity of moving through dimensions, where you have a single dimension, a 2D sort of thing, and a 3D, and imagine going to a multi-dimensional space. And this is what happens if you don't do it. This is a classic where if you limit the paradigm down, okay, you think that something's going on here, right? Everybody looks at that, and what you've done is you've projected 3D into 2D space because you wanted to simplify the problem from a 3-dimensional problem to a 2-dimensional problem. But the reality of the 3-dimensional problem is that it's just two people walking by each other. Okay, so now you have come up with a conclusion based on your projection of 3D into 2D space, which was totally inaccurate. And that happens within this space all the time. And so I warn you that this will happen consistently, particularly if you try to do this sort of reduction of data into less information. That's the curse of dimensionality. This is a second example of it. It's actually online. If you go into this website, there's a great video of this where it looks like this blob in the upper right, but if you look at it from one dimension, it's actually a triangle. You look at it from another dimension, it's actually a circle, and you look at it from the third dimension, it's actually a square. And the point there is that this reduction of dimensionality from 3D space projected onto a 2D plane can give you the wrong answer. So we're going to get into classification and categorization first. So if you look at this simple chart, you have supervised learning and unsupervised learning. And then on the left-hand side, I think it's cut off, but it says discrete and continuous. So discrete at the top and continuous on the bottom. So regression is really continuous. Talked about at the beginning from a statistical standpoint. You're trying to get a line, and maybe that line has to do with things like whether on the left-hand side is an example. Well, I actually have an example in here, so we'll get to that in a second. So we're going to talk about clustering, classification, and categorization. That's just to impress you with all the great, really math type stuff. Now, actually, from a so Bayes, naive, by the way, if you hear that within machine learning, naive just means that you're making some assumptions. And the naive Bayes method, Bayes being a probabilistic way of doing machine learning, naive Bayes is assuming that everything where you create these probabilities that it's something. So for instance, you have a probability that if a person has a weight or a height of over 6'4", you have a probability that that person's a female or a male. Right? So you have a probability function about it. Well, there's other ways to detect that also. So length of hair, for instance. There's certain biases we have would associate a conclusion. Well, a Bayes naivety is that these things don't have anything to do with each other. Right? I'm going to skip that. So linear classifier, we talked a little bit about. The function in a linear classifier could be just a function which is a function of a line, and you could though use a function which is a nonlinear function, and a nonlinear function in neural networks and in Bayesian probability and in most of the mathematical pieces is actually something that's called a signum function, which goes up and it's not like a square wave. It kind of goes up and then it rounds out. It's an S curve. Okay, and the reason why you do that is that that's a nonlinear function that allows you to do some interesting things. If you think about it in sort of two-dimensional space, okay, you can use a function like that and you can squeeze it out and move it out. It's kind of like taking sine waves, putting them together and making any sort of waveform that you want. You can use these signum functions in multi-dimensional space in order to separate these clusters of things. Okay? And that's really what neural networks and Bayesian probability statistics and all these other machine learning algorithms most of them are doing, which is basically trying to distinguish between a group of items on one side and a group of items on another in a multidimensional space with these little functions that you're going to add together. And those functions may be represented, for instance, in a neural network. So you can see here where the training set is on the left, the test set is on the right, and look at the error, 0.156. And in fact, this is a perceptron learning algorithm, which is a really simple algorithm to implement. A lot of them are online. Azure has a perceptron learning algorithm that's available. You can put a test set in from theirs and sort of just dork around with this kind of stuff. Well, interestingly enough, here's logistic regression, which is another type of learning method. It's actually very fast. And look, the error rate is comparable to the perceptron learning algorithm, but this algorithm from an implementation standpoint is probably 10 times faster. Okay, so really there's also a certain level of art with choosing these kinds of functions. Interestingly enough, there's also mapping. And so, like in this particular case, you look at that and, well, how the heck am I going to draw a straight line or even a signum function or some other complex thing in order to separate these two things? But if you go back a little bit to some mathematics that you did maybe in high school, you remember when we went from a Cartesian coordinate system to a polar coordinate system? You can do those kinds of transformations, right? So if I take that and I go, well, I don't want a Cartesian coordinate system with an xy. What I really want is a radius and a theta, some sort of an angle, right? And if I had a radius and a theta, could I separate that stuff? I could probably separate it with just a radius, right? If it's within the radius, then it's a red. If it's outside this radius, then it's a blue. And see how we transform the Cartesian coordinates to a polar coordinate system, and all of a sudden, life changes for us from the point of view of training the system. So you have to be very careful of those transformations. But there are automatic techniques to be able to do some of those things. I have 4 minutes left, so I'm going to zip through some additional slides, and I really want to get to, so nearest neighbor is one very simple algorithm to be able to do this. This is one where you basically say, oh, okay, well, I've got a test set and I've got a real set. The test set basically says, oh, okay, well, these things are red because they're close to me. These red things are close to me over here. So if I put a test character in there, I basically go, oh, okay, well, what's close to me? Oh, well, then I must be one of those guys. Okay, so it's a nearest neighbor algorithm. It's basically very simple to learn. And you can see that there's 2 nearest neighbor, there's 3 nearest neighbors. You do an average, or maybe you do a voting on them, things like that. So there's an algorithm. Here it moves into 3-dimensional space. We talked about logistic regression, naive Bayes. Let me get to some more interesting ones. We talked about that one. Decision trees. So in decision trees, what you're trying to do is trying to split the space up. And you can see how, in this particular case, if you look at that, the patrons that are going to a restaurant are very different in their aspects. So that's good because you're getting sample sets of information, or you're selecting criteria from a patron standpoint, which makes them different. If you look at that space, how would you split that up? How would you split that up? How would you take that and go, oh, okay, I want to break it up into small pieces, and each one of those pieces has certain categories? Well, there are training algorithms which allow you online, tree algorithms, forest algorithms, and jungle algorithms. They're all in Microsoft Azure, that allow you to go, oh, okay, there's the first one. And then you go pass it through again, and it goes, oh, well, there's your second one. And you pass it through again, there's a couple more. And see what happens is it splits up the space into the minimum number of groups for you to be able to do this level of classification. And the machine will do that for you with the training algorithms. Neural networks are pretty interesting because you can get a lot of classification through not very much computation. But the coolest part about the neural network stuff is that it's very nonlinear, which means that a neural network doesn't have to break the space up like the binary one that you did relative to the tree algorithm that you talked before. This one basically, when you learn a neural network and do the back propagation, once again available on Azure, with a good training set, you can get a classifier which has the capability to be able to discriminate the right-hand side, which is a relatively complex selection. So then there's these little things called support vector machines, which are really a higher order version of the regression analysis. There's Bayesian, which is based on probability. And then real quickly, from a regression standpoint, we talked about that. And then clustering. And in clustering, really what you're trying to do is you're trying to take a bunch of stuff you don't know about and basically have it automatically come back without a training set of what is like the other things. And there's a few different clustering algorithms, for instance, that are available on most of the machine learning platforms, particularly Azure. And you'll see things like k-means and spectral clustering algorithms that you can basically put in a set of data and find out what the clusters are, and then you put in another set of data and it'll tell you what it belongs to. So in the healthcare example that I gave before, that's exactly what we're doing. And that the ability to be able to take a whole lot of information about 150,000 patients that have been through, and then you take another patient that goes through and you go, you know what? This patient is a lot like that patient. And that's called unsupervised learning. And anomaly detection is really taking the cluster thing and looking for the ones that aren't in any of those clusters, right? So you take one in and it doesn't fit one of the clusters, that's an anomaly. Okay? And that's why like fraud detection is a good example of anomaly, because you've got certain transactions that are happening. The other one was the telecommunications example that I gave before, which is you have a bunch of different things that are basically, these are all the things that are sort of, moving around and they're clearly in a car from a telematics application. These things are clearly things that are operating like a burglar alarm system. And here's one item over here which is acting wacky. It must be something where there's a problem, because it's not one or the other. It's probably somebody that ripped out the SIM and decided to stick in their laptop. And now you're going to get a bill for $10,000. So I have 2 slides left. This slide is actually from the Azure website, and I highly recommend you to start there. They've got many of the learning algorithms are available. They have test sets of information to be able to do it. It's relatively straightforward to just dork around with it. And most of the algorithms that we sort of talked a little bit about today are in there. So for instance, there's lots of regression type tools, and you have ordinal regression tools which have to do with rank ordering. Like for instance, when you want to find out who the best server is in a restaurant, that's the type of tool that you would use. A regression analysis, ordinal, you give information about all the types of bills that they've done and the tips that they've made. You put it into the system and you can come out and get an ordinal ranking of those folks relative to their performance from the number of hours that they've worked and things like that. Now there's other data, right? There's data like if they got bad shifts or they got bad tables, or they got other things. So there's other data that you can put into that data set in order to get better information out from a modeling standpoint. But in addition to that, from a clustering, they have a k-means algorithm inside here, so you can have the opportunity to be able to put in a bunch of data that's just, just kind of not random data, but data that has clusters in it. You could even create it in a spreadsheet, take it, make it into a data set, output it as a CSV file, import it to Azure, and then run k-means on it, and find out whether it groups them into clusters for you. And it's kind of cool because what you're doing then is you're kind of getting an idea of how you can apply the machine learning. And then here's I didn't create this. This was Dr. Jason Brownlee that created this, but this is a mind map. I love mind maps because it gives you a way to sort of structure all of this information that I'm trying to drive at you in 30 minutes in your head. Okay, and in this particular case, I thought this was a very well done mind map because it not only talks about some of the deep learning systems like Boltzmann machine that I talked about before with simulated annealing, but it's also talks about neural networks and some of the rule-based systems and regression-based analysis that, from the statistics side, and then also decision trees and clustering. Most of these, frankly, are ones that are available through the Azure platform. Thank you.
I guess I have one question. If you could just explain, you're showing how Azure does this. I wonder if you can explain how your company facilitates that. How does your company get involved in implementing this especially for the industrial cases that we're talking about today?
Sure. So typically the first thing that has to happen is that you have to get the data in such a fashion that you can then do something with it. And so as a company, what we do is we go in as a systems integrator, look at all of your different data sources, try to figure out how to normalize them. Many of them are data sources which may not exist yet. So for instance, in the theaters, they have a little red button that you push. And then that button basically starts a timer, and the timer is how long it takes for a server to get to your seat in order to take your order. And so all of that information was available on a server because it's being put up on a map, and so we basically attached a device to it to be able to transmit that information back through the internet, through a wireless connection and back, to be able to get back. So in the healthcare example, for instance, when you take your blood analysis, the blood analysis was being evaluated locally. Now we push it to the cloud. We can do some additional analysis, but now we have that data relative to you. We do some processing in the cloud using things like Spark, which is, if you've heard of Hadoop, which is a parallel processing capability to be able to do batch type things. Spark is a almost real-time capability to do the same kind of a thing. And so what we do is we basically create a data lake for you and then create interfaces and APIs to that data lake to things like Watson, Azure, and other things, and then provide the output to be able to make some intelligent decisions.
Super. Any other questions for Jeff? I think we have a couple.
Oh, okay.
Can't get out that fast.
No, well,
I got a question about the visual. So using cameras to identify anomalies.
yep.
Have you, how success rate on the training?
Yeah, you know, so there. The nice thing about, like, for instance, Watson, is that it has a lot of facial recognition, and there's also a Python library which is very sophisticated relative to that. So one of the things that we're doing for large soft drink manufacturers, you know, those coolers that they have. Well, they have to do planogram compliance. Okay, and so putting a camera on the door so that when you open the door and put an accelerometer in there, so at 45 degrees it takes a picture with a wide-angle lens. Now you have a picture of the entire plane of that cooler. Okay, and now you basically take that, send it up to the cloud, have it processed to be able to know that you know, water is here and, you know, Gatorade is here and things like that. And if they're out of compliance, they get fined. And so they want to know whether they're in compliance or not. So that's an example of some of the capabilities where you don't have to go out and invent image processing algorithms to be able to, they're available to you, and be able to really apply them in the cloud to be able to do that processing, because it doesn't have to be done locally anymore. Yeah.
You had mentioned earlier about a use case with SMS messages for IoT. What was the specific analytics that you were looking at in the SMS messages, and what were you trying to derive from that?
Yeah, so the specific was the first, how many messages that were coming. So it was really a frequency of messaging. And then the types of messaging. So for instance, is it trying to connect to the network? Is it, you know, in SMS, as you probably know, in SS7, you're really doing a query to the HLR, right? And then you get back messaging around that HLR, and all of the signaling information about that particular transaction has a lot to do with whether or not the thing is sitting still or moving. There's a lot of characteristics you can know from an IoT standpoint about that device based on the way it's just doing its signaling and not necessarily the data that it's transmitting.
So you weren't looking at the payload, just...
No, we weren't looking at the payload at all.
Okay, we have time for one more question.
And with the data you're using right now, are you usually mostly unitary data, or are you at the point where you've got to combine data to create new predictors?
Yeah, you combine. We take data from all the different sources, try to get them orthogonal, like I said, but the data could be by unitary, you probably mean like binary data, you know, rather than is it like floating point data. And the answer is, you know, regression, and the output is a floating point number. You better have floating point stuff that comes inside, although some of the algorithms from a regression standpoint have the ability to be able to use binary data but still give you a floating point result. And the Bayesian probability statistics can do the same thing. So if you have a bunch of items which are just yes, no, yes, no, yes, no, you can get an output which is a probability of whether it's going to be yes or no.
Excellent. Yeah, thank you very much.
Cheers.